Okay, last resonance video for this week is going to be about stable resonance structures. What makes a good resonance structure? Now that we can make whatever resonance structure we want, what makes a good one? So there are examples in a lot of the worksheets that I ask you to draw resonance structures. Usually what I'm looking for is for you to draw the most stable. Sometimes it's just kind of practice moving electrons around, right? So in order to do those types of questions, we need to know what are the rules that make a compound or make a resonance structure good, right? What makes something worthwhile or stable and all that other good stuff. Okay, so strategies for good resonance structure drawing. Um, good resonance structures. Okay, first, why are resonance structures good? Um, more resonance structures equals more stability. All right, so someone needs someone needs to keep a running tally of how many times I say this is the most important thing I'm going to tell you in organic chemistry, because I'm going to say it a lot, but this is the most important thing I'm going to tell you in organic chemistry, right? More resonance structures equals more stability. Anytime we talk about structure, reactivity, anything like that, we're always going to move in organic chemistry. We always try to go for something that's more stable, right? A lot of what I'm going to ask you guys to do in this semester is justify why something happens, and we're just going to talk about what are all the rules that make things more stable, right? So we're going to talk about what makes a carbocation more stable, what makes a resonance structure more stable, what makes an acid more stable, a base more stable, an alkene, alkynes, and then we're going to get into substitution reactions. All of these are based on this idea of we're moving towards a more stable product. And resin structures are no different, right? So when I write down all these rules for what makes a good resin structure, what I'm really talking about is what makes something more stable. Okay, so the first thing is distributing charge, right? The more we move charges around, the more stable the molecule is. So distributing charge results in a more stable molecule. Right? So we've seen a couple examples where I move charge around, right? I had a carbocation that went from C3 to C1 in the previous video. That's an example, right? Because what we have is we have two places for that carbocation can exist. It can exist either on C3 or C1, depending on the resonance structure. And so if that's true, then that means that the charge is more distributed and therefore more stable. There are a couple of sub uh, lessons here. The first one is we want to have less separation of charge. Separation of charges, less equals better, right? If we can have the minus and the plus close to each other, then they can kind of stabilize each other by attracting each other, one being negative and one being positive, right? If they're very far apart on the molecule, they can't really stabilize each other as well. And so the closer, when I say separation of charges, I just mean the closer the charges are to each other, the better in general. All right, the second thing is if we have a choice, we want to put negative charge on more electronegative elements. Right? O minus is good, N minus is okay, C minus, not good. Right? If you have a negative charge that you're trying to move around, that you're distributing with your resonance structure, the most stable resonance structure will probably be one where that negative charge is on some kind of heteroatom, like oxygen in particular is very electronegative and very good at holding on to negative charge. The opposite is also true, right? Positive charge on less electronegative elements. I should make sure that this is clear. This is all part of this thing, right? And so positive charge would be in the opposite direction, right? Nitrogens are going to be better than oxygens with positive charge on them. Oxygen is going to be better than fluorine with a positive charge on it. Right? Now, I purposely didn't mention carbocations because that's the last thing about avoid carbocations if possible. Right? And the reason behind that is carbocations don't have a full octet. Not a full octet. Oh my goodness, octet. And so carbocations are incredibly unstable because they're short electrons, and so they want to find those electrons, right? So if you can draw a resonance structure that eliminates carbocations, that is usually going to be a really great result. Right? It's not always possible, right? The example that we did in the previous video where we have positive charge here, no matter where we move this around, there's always going to be positive charge. And because we only have carbons for that positive charge, we don't really have any choice but to make a carbocation. And so if we don't have a choice, then we have to make a carbocation, and that's going to happen. But if we can avoid it, if there are ways out of it, for example, if you were looking at these two structures and trying to decide which one is the more stable resonance structure, right, the one that has the carbocation is never the answer, right? The most stable resonance structure is going to be the one that does not have a carbocation in it. Okay, so distributing charge is good. And we want to do that by putting negative charge on more electronegative elements. We want to avoid carbocations if possible. It's not always possible. And then what are some other rules? Make pi bonds if possible. More pi bonds equals more stability. Okay. So if you can make additional pi bonds, we saw an example of this just on the, we just saw this, right? If you have, there we are, right? If we have this one, and we make a pi bond with that, there's a couple of reasons why this is more stable. One, obviously you've gotten rid of charges, which is usually good. Neutral is always good. But two, we've created a new pi bond, and so we have more electrons in covalent bonds. That's going to make things more stable, just because pi bonds are always going to be less reactive than lone pairs. A clue for where to start, right? And so we've talked about this. So good resonance structures start from heteroatoms with lone pairs. Oops. Or pi bonds. So when you look at a structure, when you are doing a worksheet or whatever, and you're looking at a structure and you want to draw a resonance form of it, find those lone pairs, find those pi bonds, start there, and then think about where you want to move them. And where you want to move them is you want to distribute your charge if you can, right? You want to avoid making carbocations, you want to make pi bonds if you can. Put negative charge on the more electronegative atoms and positive on the less. So those are the rules to kind of guide you where to move stuff. Now, there are always going to be exceptions. There's always going to be ways that are going to force you to break one of these rules in order to satisfy the others, right? And so the answer to the obvious question is always like, which rule do I follow the most? And the answer is you try and satisfy as many of these rules as possible. And if you have to break one to satisfy a couple others, then that's allowed too. These aren't hard and fast rules, these are guidelines. So make sure that you practice the resonance on there. If you have questions on those worksheets, bring those to class, bring those to office hours and all that good stuff. But I think those are the main points of resonance that we're going to tackle this week. So we should be more or less done with these resonance videos. Okay, Next, I think there's some stuff on conformational isomers, which is very much different from everything we've talked about so far, but another type of organic structure thing that we need to cover. So look for those, and I'll see you there.